Welcome back. So where I left off, we said that I was going to throw a ball, and I threw it at an angle of 45 degrees to the ground. Let me draw the ground in green, as hopefully the ground is. That looks more like green water, but I think you get what I'm saying. So I throw a ball at a 45-degree angle, and I throw it at, what did I say? Oh, I think it was 10 meters per second. And I want to figure out, let's say the problem is, I want to figure out how far does the ball go, or how high does, or not how high, well, I could figure that out as well, or how long does the ball stay in the air. And what we said is we can break this vector. This vector says, has magnitude 10 in the 45-degree direction. We can break it into its vertical and horizontal components. So its horizontal components, this horizontal component would be this vector, and its vertical component would be this vector. Whoops, I know the other way around. It's vertical and horizontal are always the two things that I found most confusing. Its vertical component would be this vector, and its horizontal component would be this vector. Sorry for confusing you. And so we could treat it just like the sides of a right triangle, because as we know, the vertical is perpendicular to the horizontal. And what I find very fascinating about that is that we're dealing with the velocities, and we can still treat them like they're the sides of a right triangle, and that's why vectors in general are so useful. And as we do more problems, hopefully you get more of an intuition. And we said from the previous problem that, well, not the previous problem, the previous presentation, that the length of this side, if you just use your basic trigonometry, would be the vertical component of my velocity. So that's v sub v, so v sub vertical, which is an unconventional way to write it, would be 10 sine of 45 degrees. And that equals what? What's sine of 45 degrees? That's square root of 2 over 2. So that's 10 times square root of 2 over 2, which equals 5 square roots of 2. Right? And the horizontal component of my velocity is 10 cosine 45 degrees. And once again, to figure out this and this, we just use SOHCAHTOA. We just said that the vertical velocity over the hypotenuse is equal to the sine of 45 degrees, and then we just rearranged it to get this. And we said that the horizontal velocity over the hypotenuse is equal to the cosine of 45 degrees. And then we solved it to get this. We solved for the horizontal velocity. And then this also equals 5 square roots of 2. So what can we do now? Well, this is what I find to be the really interesting part. If we wanted to figure out how long does the ball stay in the air, the only thing that's keeping the ball from staying in the air forever is gravity, right? Gravity is what's bringing the ball back down to the ground, and gravity only works in the vertical direction, right? Gravity only works. I don't like this color. Gravity only works in the vertical direction, always pulling directionally down. Always pulling directionally down at 10 meters per second squared. So what we can do is we can break this problem up into two problems. We can say, well, this ball is going to stay up in the air just as long as a ball that was thrown straight up, as a ball that's thrown straight up with the same vertical velocity. This ball is going to stay up in the air for the same amount of time as something thrown up straight up at 5 square roots of 2 meters per second. And I want you to think about that, because that's actually, at least when I first learned it, wasn't intuitive, and the more you think about it, it kind of becomes intuitive. And then you might want to experiment with it. A ball that's thrown at an angle will stay up. Well, let's say a ball that's thrown at an angle that gets as high as, let's say it gets as high as 500 meters. Let's say I throw a ball, and this is the motion of the ball. So let's say this is the path of the ball. The ball looks like this, right? And let's say the highest point that the ball traveled, let's say this is 500 meters, right? That would be but more like a cannonball or something. I can't throw a ball 500 meters high. So this is the ball that's actually thrown at an angle, right? It travels some distance along the ground. What I'm saying is that this ball is going to stay in the ground, is going to stay in the air the exact same amount of time as a ball that does this. And this is 500 meters. That's interesting. So it doesn't matter what the horizontal It doesn't matter what my horizontal. The difference between these two balls, and I should probably use different colors. The difference between this ball, which is thrown at a steeper angle, than this ball, which is thrown at kind of a more, it looks almost like a 45-degree angle, is that this ball's horizontal velocity, its velocity in this direction, was lower. This ball had a much better horizontal velocity. But the time that they stay in the air, and once again we're assuming nothing about air resistance or anything, the time they stay in the air is exactly the same. That's really interesting. Another way to think about it is if I'm on a cliff and I just drop a ball and it just goes straight down on a 500-meter cliff, that ball is going to take the same amount of time to hit the ground. It's going to take the same amount of time to hit the ground as if another ball that was moving, let's say it was moving, it only had horizontal motion. So the second ball goes like this, right? So it moves along the horizontal axis the whole time. So it's moving to the right the whole time while it's falling. But both of these balls, let me draw the second ball in magenta. The second magenta ball is going to take the same amount of time to hit the ground. And that's because its vertical velocity at any given time, its velocity in the downward direction, is going to be the exact same. And that's because gravity is only pulling in the downward direction. I want you to think about that a lot because that's kind of a core intuition of vectors in physics, is that you can break out the velocity into horizontal and vertical components. And that once you do, kind of the things that are affecting it in the vertical component are identical regardless of what's happening in the horizontal. So that might have been helpful. It might have confused you further, but let's just continue on with the problem. So let me put this a little bit on the side. I took too much space. I might have to. So my vertical velocity is going to be 5 squares of 2 meters per second up, right? And we're going to stay with the convention. Positive is up and negative is down, just like in the coordinate axis. So how long is it going to stay in the air? If I threw a ball straight up at 5 squares of 2 meters per second, how long is it going to stay in the air? Well, the way I think about it, the easiest way to think about it is the same amount of time it takes to go up is the same amount of time it's going to take it to go down, right? We learned that in a couple of videos before. So how long is it going to take it to go up? Well, to go up, it's going to start at this speed, 5 squares of 2, and then at the top, when it's at the top, it's going to be going, it's going to have 0 speed, right? It's going to have 0 speed, so it's going to decelerate from 5 squares of 2 to 0 in some amount of time. And here we could just use the very simple equation. Change in velocity is equal to acceleration times time. Well, what's the change in velocity? It's the final velocity, which is 0, right? It's the final velocity, 0, minus my initial velocity, minus 5 square roots of 2, is equal to the acceleration, that's 10 meters per second squared, and forgive me for not putting the units in right now because I'm running out of space, times time. So if we solve for t, we get, the negatives cancel out, right? The 0 doesn't matter. So we get t is equal to 10 over 5 square roots of 2, which equals 2 over the square root of 2 seconds, right? T equals 2 over the square root of 2 seconds. And of course, if we wanted to rationalize this, we can multiply the top and the bottom by the square root of 2, and you get, well, actually, you don't even have to do that. What's 2 divided by the square root of 2? Well, that's just equal to the square root of 2, right? Because the square root of 2 times the square root of 2 is, of course, 2. So it takes a square root of 2 seconds. But is that the total time that the ball's in the air? No, that's the amount of time it takes for the ball to go to its highest point. It takes square root of 2 seconds, right, to go to its highest point. But then it's going to take the exact amount of time to come back down. So the total time in the air is going to be the total time in the air, and I know I'm doing this very messy. The total time in the air is 2 square roots of 2, just 2 times this. Because it takes the same amount of time to go up as it does to come down. And it might be confusing, but all I did is I figured out the vertical component of the velocity using some basic trigonometry. And then I said, well, it's going to decelerate with gravity. And over that time, when it's going up, however long it takes, it's going to be going from that 5 square roots of 2 meters per second to 0. So how long does it take to decelerate from 5 square roots of 2 to 0, given that I'm decelerating with gravity, given that I'm decelerating at 10 meters per second squared? It takes us 2 square roots of 2 seconds. I will continue this in the next video.